Our next presenter is Noel Khan to speak about sensitivity analysis of NASA and NASA AFRCS expandable variable anatomy architecture.
Okay, thanks. So this presentation, first of all, mic check. Can everyone hear me okay?
Yes. Yes,
Yeah.
Okay, good. So there's two parts to this presentation. The first is to kind of contextualize autonomy and NASA's autonomy framework. And then the second part is going over the sensitivity analysis to evaluate the suitability of this autonomy framework for military use cases. So first off, autonomy abstracts the control inputs. So if you're driving your car, you're providing control over the steering and thrust. Those are your control inputs. But if you had an autonomous system, you would provide like an address or a GPS coordinate, and it would work out how to manipulate the steering and the thrust in order to get to wherever you were trying to get to. And it would be constrained by, physics, vehicle dynamics, and the rules of the road. So waypoint follower is an example of an autonomous behavior that's usually implemented by like a PID controller. It takes your current position as an input, usually from your GPS sensor, and then a target position or a series of target positions. And then it'll work out, in the example of a quad rotor, it'll work out how to change the attitude of the vehicle in order to move around. Now, if you enrich the controller with additional information, like give it the current attitude and target attitude, you get a more capable behavior where you're not just going point to point, but you're actually orienting yourself so that you could jump off to the next point. And so now you could do drone racing. My point here is that adding expressiveness isn't really giving you a different behavior. It's giving you a more capable behavior. So what I'm talking about with NASA's autonomy framework is really multi-behavior autonomy. So going back to the example of you driving your car, manipulating the steering wheel and hitting the gas, imagine if the backseat driver also had a steering wheel, brake, and accelerator. You'd be fighting over control and where the vehicle's going. So the key thing is if you have multiple behaviors, you need some form of arbitration framework to decide who's in control at any time. Pictured here are examples of arbitration frameworks. They're essentially differentiated by how they coordinate control. They're either built for optimality or built for failover, and they're also differentiated by use cases. So on the far left, you've got a system that is SWaP-C constrained for unmanned systems. In the center, you've got an autonomy framework from DARPA and Lockheed, which basically convert manned helicopters into autonomous helicopters. And then on the far right, you've got Johns Hopkins system, which is kind of like Boeing's Iron Bird. So you basically field the entire system, but never really give it control over the vehicle itself. So it's just kind of in the back seat getting real world input, but it doesn't actually control the vehicle. So it's called a vehicle in the loop. So NASA's contribution in this space is a reactive control system that's all domain, terrestrial, naval, aerial, submersible, whatever. It's payload agnostic, it's behavior agnostic, and it can coordinate control within the vehicle between a pilot and whatever other controllers you have on, and also coordinate control off board. If you had a mission system that was controlling the aircraft, and that's what's meant by variable autonomy. So it's expandable in that you can keep plugging in additional behaviors, payloads, and guidance, navigation, and control systems, and it'll coordinate the control. It started out at NASA 4 decades ago, implementing like automatic behaviors on the F-16. If you guys get a copy of these slides, I'd encourage you to see this, a video of it in action. This is a ground collision avoidance recovery. But the key thing I want to point out on this origin story is that it started with manned aircraft and a manned use case. So what it needed to be was deferential to the pilot. And so this is kind of the three design goals behind the architecture don't get in the pilot's way, don't make the outcome any worse, and, you know, contribute a non-zero improvement to whatever's happening. Here's another way to visualize why that design philosophy has such a huge impact on the architecture as well as kind of the design. So typically, when you design a system in the universe of discourse, you only specify what the system will do. This doesn't work for autonomous systems because you can't specify what a system will do in every circumstance. So NASA inverted that paradigm, and instead what you do is in the universe of discourse, you allow everything. Again, this is the fighter pilot doing whatever he wants to do, except, and this is where you actually specify what it can't do. And the yellow around here are kind of the boundary conditions that tell the system that you're about to go into an unsafe control action. And so this is how this autonomy framework that NASA's developed is like autonomy enabling. It allows everything except for, you know, bad behavior. This is what it looks like under the hood. You've got the pilot, the mission system, a bank of behaviors, all fed into a moral compass is what they call it, but this is the decision module. It selects which one of these behaviors is going to get forwarded out to the autopilot. It's not only looking at external hazards, but it's also looking at internal hazards. So if there is, for example, discording sensor data, like the angle of attack sensor on Boeing's MCAS system, if there were discording sensor observations, then it actually triggers a contingency behavior, which could be a forced landing or return to base or something like that. So NASA is a civilian aerospace organization. I worked on developing that architecture for a couple years, but then the U.S. Army was interested in using this for military use cases. And so these were the research questions here. So most of what NASA was looking at, again, is civil use cases, crashing into other aircraft, crashing into the ground. These are black swan events. But in a military environment, that is no longer on the long tail of a Gaussian distribution. That's towards the belly. So in a more contentious environment, the expectation is you need more behaviors. You don't just need more expressive existing behaviors. You just need more tools in your toolbox in order to evade and all the threats that are out there. So the first question is, how many really, the point behind the first question is, how many behaviors can we add to this system before it starts getting funny? The next question is, if we wanted to deploy this system on faster aircraft, is it only a matter of deploying it on faster hardware? If you think back to one of the earlier slides, I said it's payload agnostic, it's behavior agnostic. The idea behind this architecture was that you can actually create plugins as a capability, keep it on the shelf, and then depending on what mission you needed, you would pull a bunch of plugins off the shelf, deploy it on your system, and then it would have the behaviors it needed for that mission. So in other words, reuse is kind of is baked into this architecture. We're assuming that you can reuse a air collision avoidance system that's useful for aircraft on, say, missiles. And that's an assumption. And so we're going to test that in our research. And finally, there's this concept of process capability versus process control. Capability is how you can manipulate the system to do different things. You tune the parameters, you augment the trajectory of a vehicle, you do things like that. If the system produced the same output every single time, it would be a controlled process, but a system that can do a variety of things with some tuning is a capable process. And so as far as the first question, we took a model-based approach. We built a model that takes into account the system parameters that have to do with allocating processes. And we built this model here, and the optimal point, the fitness again, is measured in terms of not just the load on the system, the CPU utilization, and the number of processes, but also configurability. On small aircraft, it's not so much a big issue, but on larger aircraft like a Predator, you're actually running a server, a virtualized environment. So you may not have the space and resources to deploy the whole thing on one compute node. You might have to, allocate resources. Yes.
And move to questions, please. We need to wrap up and move to questions.
Okay, sure. These slides go pretty quick. So anyway, our finding was 4 processes per core. NASA more recently actually found the same thing. As far as performance, obviously CPU has the highest impact on performance, but only to a point. So the question of reuse, being able to reuse plugins, is limited. Like you're going to want vehicle-specific plugins. We looked at the telemetry stream. It's suitable for research, not so much swarming or very fast aircraft. And on process capability, we ran about 2 million simulated runs, captured the data, and produced tables like this, which allocate parameters along 2 different axes, maneuver and response metric. These give you an idea of what effect each parameter would have on the output, but you have to consult diagrams like this to figure out how best to tune, because it's nonlinear. So that was the research. A lot of the details are in the paper. So if you're interested, check that out. Any questions? All right.
That was a wonderful presentation. Any question from the audience? Okay.
I think, Noel, they're wondering why you're presenting NASA. So Noel basically works for NASA, and he's doing his PhD with us. I think the question here, Noel, with the adaptability and autonomy, is it adaptability in real time, or is it something that you can plug in different entities or players and then have that adaptive architecture?
Yeah, so it's a soft real-time system. Each of your processes can be scheduled, separately. The kind of key thing in the architecture is that you can implement independent algorithms, and the decision module coordinates the behavior. So you can have things running at different rates, and that's totally acceptable. It all depends on, what period you need that process to run at. So for ground collision avoidance, we're running every 200 milliseconds. For air collision avoidance, it's about 40 milliseconds.